Okay, here's a brief overview of what we'll be talking about. I'll give a little mission update, and then Matteo will tell us about his results, and Fabrizio will tell us about the VIRTIS results. So I'll be quick, and we'll get on to the real important stuff with these two gentlemen. So I provide a brief mission update. I think I've been asked mostly about this fellow. We had the last contact on the 9th of July. For those of you not aware, we've also had problems with the cometary atmosphere. It's a very dusty atmosphere that has meant that we have had to move further away from the comet. That is contrary to what you need to contact the lander. So we're now beyond altitudes that we would be able to successfully contact the lander, and we believe we'll get back, well, we know we'll get back in late October time to altitudes that will allow us to contact the lander again. And we expect, hopefully again, that the lander will still be functioning in that time period. Recently, our biggest epoch, as it were, was perihelion, as I indicate here in this graphic, when we were closest to the Sun. Just before that, we had some very interesting activity. We have had a lot of interesting activity, in fact, with some quite spontaneous outgassing of material from the comet nucleus. This particular event was was in late July. The three panels show a before, during, and after shot. So within about 40 minutes, we saw an extension of gas and dust being exuded from the comet nucleus, and then it disappeared. We detected that from Rosetta, about 180 kilometers away from the comet, and it really showed a completely different environment. We saw lots of different and new material that we weren't seeing on either side of this jet or this outgassing event. It was also so strong and so powerful that it forced the solar wind, the outer atmosphere of the Sun, which is interacting with the comet all the time, it pushed it completely away. So we saw a dropout of the magnetic field of the solar wind. So that was really impressive, in particular because we weren't expecting to see this so-called diamagnetic cavity, this lack of magnetic field. We thought it would be much closer to the comet, and because we couldn't get close to the comet at this time because of the activity, we didn't think we were able to measure it at the moment. And thankfully, the comet helped us by bringing the magnetic cavity out to us. On the at perihelion, I show this image here, which I hope is rotating behind me. Yes, it is. A bunch of frames from the OSIRIS camera. On the 12th, you'll see, again, there's lots of activity going on. And this is persistent. We're seeing this a lot, even through, so this was August, and now into September with some NavCam images. We're seeing more of that occurring now. At the moment, we're travelling out towards 1,500 kilometres away from the comet on an excursion to try and look at the bow shock of the comet. Again, looking back and where I was discussing the magnetic cavity, how the solar wind, the outer atmosphere of the Sun, is interacting with the comet nucleus. And this supersonic solar wind has to be shocked to slow down to then be diverted around the comet. And that's what we're looking for with this excursion. We'll get back to closer altitudes around mid-October, as I said, around 500, 400, 300 as we step closer towards the comet. We were nominally going to last until December this year, but we had a mission extension that was successfully accepted by the committees of ESA, which means that we will run operationally until September next year. Ultimately, this period of time will allow us to do new science, more science, as the spacecraft and the comet move further away from the Sun, to get the best picture we can of how this comet is working with respect to the Sun and its interaction and heating, etc. The end of mission scenario will be to spiral the spacecraft into the comet, which I thought was going to do that. It's not spiraling, is it? There, it's spiraling now. And that will be our picture, as it were, this time next year. So in September, well, August and September next year, the focus will be on this end of mission scenario. We'll gradually go from about 10 kilometers and step down closer and closer. And then that will be the end of Rosetta. And we'll be landing for a fourth time. So in summary, perihelion marked the beginning of the end of the mission operationally. But scientifically for me, and I think all the teams, it's only just begun. We've had a number of journal releases. They're starting to flow. The science is starting to flow from the mission, building our knowledge of this particular comet and its place in the solar system with all the other comets. And I think the science that we're generating now will provide scientists a lot of activity for many years. That's the whole point of doing this, after all. Today, we'll hear some expert opinion of some of the latest results from Rosetta. So I'll hand over first to Matteo, so hopefully my transition skills will work here.
Okay. I will talk about this story, the story of two independent and primitive envelopes of the bilobate nucleus of Comet 67P. It is a beautiful story. Like all the beautiful story, it has a happy end. So let's see further on. When we saw this bilobate shape of the comet, the duck shape of the comet, we see the body, which is the major lobe, and the head, which is the lower lobe, and you can see them in the upper left. And the main questions were: do this particular shape is this particular shape due to erosion, enhanced erosion in between the two lobes? Is this particular shape due to the junction of two different objects at the beginning of our solar system, or is it the results of the merging of several pieces derived from a large parent body that was destroyed and then merged again? So in our first observation, we have seen in the lower left, you see, we have seen several morphologies indicating the presence of terraces at different levels. And looking from above, and you see it on the right, you can see that these terraces actually seems stratoplanes. And at different levels, you can go, okay. And the strata are here shown in green, and in red are the boundary of the strata that are in red. We have also taken into consideration the shape model. When we have the shape model, the photogrammetric shape model made by the DLR people of our team, we have seen that these strata as different are aligned along different elevations. So actually, these terraces are actually representative of strata. In addition, you can go on. We have seen these pits that was one of the important findings of our mission that were described some months ago in a Nature paper. And these pits are very deep, 200 meters of depth, 200 meters of diameter, and inside the pits, you can go, we see that we have still a stratification, and this stratification is visible inside the pit and on the wall. And this stratification is also thick, because you see on lower right, you see the big terrace and the wall, and it is a 400-meter high wall, completely stratified, and also in the lower part there is another wall 300 meters, and there is also walls of 900 meters completely stratified. So a stratification that is very thick and is representative, a primary structure, internal structure of the comet. And if we look in the general surface structure, we see that actually there are partial envelopes of the stratification. Here we see a stratification separating two region sets and atom region, and we see that this stratification are showing partial envelopes. And this is for the body, but also for the head. We can go on. And here we have the stratification that is showing still a partial envelope between matte and Hanukkah, and also high resolution images in which we see these terraces in an arced shape attitude. So all of these are suggesting partial envelopes. So we can see other images in which really these partial envelopes recall us an onion-like structure. So we can compare it with an object which is characteristically as an onion-like structure, so an onion. So we see the striking similarity. I'm not saying that the comet is an onion, obviously, but I'm saying that the structure are very similar. The internal structure are very similar. But we don't know how continuous are strata. We didn't know how thick are these strata, and the relationship between the strata of the body and the strata of the head. So we have to take the shape model, we can go, that has been produced by the member of Laboratoire of Astrophysics de Marseille of our team, and we have fitted in all terraces with best fitting planes, so with the strata. We have taken more than 100 strata in order to have an idea of the orientation of the strata in each place of the comet. And what we have seen is that this stratification is really continuous, and the stratification of the body doesn't match with the one of the head. So they are really two distinct objects, but we still do not know at the moment. We still didn't know the thickness. So we had to cut across the comet, and like when we cut across an onion. So we are not sure of the onion structure of the onion if we don't cut across it. So we have cut across the comet with a plane. We can go. And so this is the green plane. This green plane on the upper left is cutting along the major axis of the comet. And we see the strata nearby in red, and we have projected this strata into the plane. And we have obtained in the lower right this topographic profile of the comet with the strata, the measurements that are these double arrows, blue arrows with a green one, which is the orientation of the strata at that point. So knowing that strata are parallel one to each other, we can draw the inner stratification of the comet and make a real geological sections. And on this geological section, we have seen that the strata, the two lobes are characterized by onion-like inner structure, at least up to 400 meter on average. In some places, we reach 650 meter of a stratified sequence. In other, due to the variable topography of the comet, we have smaller, thinner stratification of 150 meters. So, and we have cut the comet also across planes that are perpendicular to the major axis, and here we see again the onion-like structure of the comet and the thickness of these onion-like structures. And this is another line of evidence that the two objects, the two lobes, are two different objects. And then we have passed to the gravity, so we can go on. And here on the left you see the these green lines on the comet are the gravity vector in each place of the comet. And we have calculated, we have measured the deviation between the direction of the gravity vector and the perpendicular to the strata. So how the strata deviates from perpendicular with respect to the gravity vector. But the gravity vector were calculated for the complete comet, the bilobate shaped comet, and for the two distinct objects. To the right you see the diagrams, histograms and curves. You see in gray the model related to the two distinct objects, and in black and dark gray the model related, the gravity model related to the results of the gravity model related to the complete comet. And you see that the deviation, the angular deviation from perpendicular, is very low for the model of two distinct objects. So this means that the stratification that should be perpendicular to the gravity has to be formed before the junction of these two objects. And so these three lines of evidence lead us to the happy end, which is the last image. This is not a scientifically correct image. I like it very much emotionally, actually, but because give it the idea of the happy end. If someone wants to see the model, the real model can be visible from the Jutzi and Aspau paper published in May in 2015, this year. But here we see that we have to imagine a long time ago, at the beginning of our solar system, the head met the body, they gently merged together, and for billion years afterward, up to date, they follow their path strictly joined together. So it's quite, I would say, quite beautiful love story.
Thank you.
Yes, thank you very much. Yeah, this will be an update on the paper which has been published last week in Nature concerning the diurnal cycle of water on water ice on the surface of Churyumov Gerasimenko as observed by the VIRTIS instrument. And the paper was published last Friday, and this is the issue of Nature. And we have an update on that. The work related to this paper was done some time ago, and then go through all the review process, and in the meantime we have additional results which confirm what we observed. But first let me go through a brief description of the VIRTIS instrument, which is the infrared and thermal imaging spectrometer, visible infrared thermal imaging spectrometer on board Rosetta, and had two main goals, which is to study the nucleus, the surface composition, and the surface temperature, and also to study the coma, gas and dust. For the coma, we study the major molecules, the abundance of the major molecules in the coma, and also we study the dynamics of the coma and the gas and the dust. VIRTIS, to do this, is made of two different channels, and there is a consortium which have produced the instrument, which is responsible for running the instrument in Italy, France, and Germany. And then, of course, there is the national funding agency and industry which has been involved. Let's go to the real summary of what has been observed and what is described in that paper. There was last week a blog of on the ESA page, and there was a press release. So this will be a brief summary of what we have been observed and described in that paper. On the left, you have an image of the navigation camera, and there is a red square which marks an area of the nucleus, which is in the neck, where we observed in subsequent days three different we had three different images taken, spectral images, in which it's clear the variability of the abundance of water ice. And if you go to the next one, here we have some additional information. From the spectral data and from the temperature data, we retrieved first the abundance of water ice. And on the left, you have three different panels from top to bottom, which display the abundance of water from dark blue, from black through blue and to white, in the different observations, which display the decrease in abundance of water ice going from white color to the dark one. On the right, we have the temperature, which has been determined from the VIRTIS results, and again for the same areas. And the temperature is seen to decrease from white to the reddish part. And if you see in the image, the relation between the two is inversely proportional. That is, when we have an increase in the temperature, we have a decrease in the water abundance. The next one is also shown the same thing, and and in a plot form. So on the abscissa we have the temperature, and on the ordinate we have the ice abundance as derived from the previous observations, from the previous slide. And what we see is that increasing the temperature, the abundance, the amount of water ice is decreasing. So from this we derived some additional information. That is, we derived the way the water vapor is transported to the next one, is transported to the surface. Everything is driven by the low thermal inertia of the body, of the first layer of the body, the first few centimeters of the body. This was observed already since the beginning of this year when we performed the first observation. The thermal inertia is a property of the material which is related to the capability of the surface material to react to thermal variation. The lower the thermal inertia, the faster the body is able to change its temperature accordingly. And so what happens in this case that we have a very thin layer, few centimeters, in which the material is dusty and has a low porosity and low thermal inertia. This means that as soon as the insolation changes from morning to afternoon and to night, the temperature of the surface layer changes very fast because of the thermal inertia, and the lower layers are warmer. So the sublimation from the lower layer continues, sublimation of water, which is what drives away the water vapor. And when sublimate goes toward the surface, and at the surface it finds an upper layer which is colder, and then recondense on the surface. So you have a sublimation gas formed from ice at deeper layers, and then recondensation at the upper layers. And this is summarized in the next slide, in which we give the overall cycle that we made hypothesis on. In the first upper left cartoon, we have, as I said, the thermal heat wave from the sun penetrate deep in the surface and produces sublimation of ice. And during the day, this ice transforms in water vapor and is lost in the atmosphere, in the coma of the surface of the nucleus. When you go into the afternoon or in the shadow or in the night, the upper layer react very fast to the surface variation, the insolation variation, and cools down in such a way that the sublimation from below is somehow trapped, and then you have recondensation on the surface. During the night, everything stops. And then in the morning, this process starts again. And the first material that sublimates in the early morning is the ice which has been trapped in the few centimeters up in the upper layer. And this is what we observe. We observe that the amount of water ice content into the first few centimeters follows the temperature variation. Following those observations, we have been looking at the surface to study the diurnal variation to monitor the evolution of the water ice on the surface. And we have summarized all the observations we have done in the period August and February. This will be presented tomorrow by Mauro Cerniello in his presentation in the Rosetta session, and this is summarized in two movies which I will describe immediately after. These projection and the movies and the projections of our observation on the shape model provided by the OSIRIS team has been made by Angelo Zinzi and by the ASI Data Center in Italy. So if we go in the next one, this is a description of what you will see. This is a still of the movie that we will see later. And this is concentrated in the neck region. The blue areas are those which are icy, which has a high, relatively large water content. And in the reddish, we have no ice, and the shadows are in green. And below you have the time of the day in 12 hours, which is the overall day of the surface, the duration of the day on the nucleus. And you need to concentrate in the central area in the neck, when you will see that going from shadow to morning, there is an increase in the blue, and immediately after this wanes out, because the eyes disappeared as the insolation increases. If we move to the next movie, yeah, should start. Yeah, again, this is run a couple of times, and the second time will be slower. Here it is. You see that as soon as the illumination hits the surface, the sun hits the surface, the surface, the part is not more in shadow, and we have a bluer region. This is not always, not all over the surface, but essentially around the neck. And you see that as the time progresses and we go into the day, the presence of the eyes decreases. We have another view, which is in the hemotep region, which is at the bottom of the. Maybe we can take the model there. Yeah, is exactly at the bottom of the body, let's call it. And here again on the bottom left, you will see for a very short time there is a small region on just on the tip of the foot, exactly here. You have one region in which you have a sudden increase in the amount of eyes, and then immediately after a decrease. So if we go in the next one, you will have the. Here we go. Yes, it's all just 2 frames. If you look on the bottom, yes, right. Then we have water, and then we don't have water anymore. And this is essentially the area in the hemotep which has this variable performance. Then there are other areas in this region in which you have a permanent blue color, which means that there is ice which is stable on the surface for throughout the day. But this is part of another work, and it will be described in a subsequent paper. And that's it.
Okay, thank you both. I'll hand back to Anita now, I guess, to chair any discussion or questions.
Okay, so does anyone have any questions? Okay.
Hi, Lizzie from Nature. Matteo, can you tell us any more about the origin of the 2 pieces that then we think came together? What do we know about them, and were they made in the same place or different places, and could they have been part of the same larger object that was smashed to pieces and brought back together?
Okay, actually, these 2 pieces were, what we know is that even they were probably not formed in the same place, they were formed in the same way. So the main thing is that we are looking to the process of aggregation of comets, and up to date there were no clear models showing that comets can aggregate following onion-like stratifications. So this is one major point, and there are some hypothetical theory explaining stratification, but they are not yet modeled. surely, if we see this stratification, which is really ordered in an onion-like structure, we have to think that these two bodies should have collided very slowly and merged very slowly. Otherwise, we didn't have this ordered structure. And also during their evolution, they avoided any catastrophic collision. And this is quite important because it depends from the mass of the planetary disk, the temperature of the planetary disk, what is happening when we have the migration of the giant planets from the inner part of the solar system to their present position. So the implications are very important, and okay, and these are actually I'm a geologist, so some astrophysicists question. We have some people here that can answer actually something about the origin of the solar system, and okay, so if you need, we can ask to go Kutler Kasten from Max Planck Institute, or they can answer some particular things about the origin of the solar system.
Okay, sorry, just before we go to you, Leo, I have a question from UK50, who's tweeted in to say, has the crack between the lobes evolved?
I can probably put the question over to the OSIRIS team, but my assumption would be that we can't tell because we're too far away at the moment, but maybe Carsten or others want to comment on that.
That's true. We hope for the next equinox to see it. No, we haven't seen any new high-resolution images to see whether it has evolved. So we are hoping for the next seasonal change for the next equinox and hope to be closer then and then compare it to pre-perihelion, see whether we see a long-term evolution.
Thank you. And could you just hand it over
thanks.
to Leo?
Leo Enright with Irish Television for Dr. Capaccioni. Just trying to understand from your model of this water cycle, would you expect that this process would shut down very quickly now that you've passed perihelion? Because if I understand the mechanism that you describe, you're talking about something which is being progressively more insulated by the sun and therefore getting deeper and deeper to the source volatiles, the water underneath, but presumably once the solar heating reduces, this process will shut off rather suddenly. And if I might, just a second question, whether this data relates, is this all from before the equinox, where before the change in solar irradiation on the comet, and do you expect other results because of that changing orientation?
Yes. In fact, these data were from September last year. September last year, we were around 3.5 astronomical units, so the distance was fairly large. In fact, we saw the beginning, actually, not the end of this process, because as the comet progressively goes closer to the sun, this effect is even stronger. And in particular, also the inclination of the axis of the comet is such that we moved from the summer in the north hemisphere, the axis, rotation axis is here. So we moved from the illumination of this area to the illumination of the southern hemisphere. So the effect should be particularly strong in this perihelion, in this summer part. One of the major issues is the distance from the surface, because to observe those kind of features, we were at around 20-25 meter resolution. And we didn't have the capability to do that later after April, May, in which we were moving farther from the surface. But the process will die when the comet will move farther away from the sun. So when we will be moving after the extended mission. So in principle, we have the opportunity to see it again when we get closer to the comet, when the activity decreases. Now the activity is too strong and we cannot get closer. So this is This is essentially concerning the fact that you were saying that the progressively the stratification is such that the volatiles move deeper. You have also to remember that even the surface move deeper because we are losing material. So in principle, we are not always at the volatiles are not always at the same distance from the surface, but the process is you have a common process of material, of volatiles moving deeper into the comet, and the comet exfoliating. So in the end, you have it's a balance between these two processes.
Any more questions? Livia, do we have any further ones from Twitter? Do you know? No. If anybody is watching this on the live webcast, they can tweet us with the hashtag EPSC 2015. I'm sure that our wonderful panel will be happy to answer questions later on. So if you do still have questions, we will follow up with them and get you those answers. But Leo, yes? Okay.
Give Taylor a job to do. Matt, if I could ask a question about this Bauschock little excursion. How long is that going to last? And when, I may have missed this, I'm sorry, I came in a little bit late. So when do you expect to be back on station after the Bauschock?
Well, we come in, I think, within about 500 kilometres again within early October. But it was basically 3 to 4 weeks we've started going away now. So I think we get at 1500 around the end of about 30th of September, the end of this month. Then we'll start coming back again. Yeah, out to 1500.
Okay. Well, unless anybody else has anything to ask, I'd like to thank our panel very much for their time today, and congratulations on more wonderful results. And we look forward to some fantastic days of Rosetta sessions here at EPSC tomorrow. So thank you very much.